And I'm saying here, watch the internet at that time. Okay, tonight's speaker is an astrophysicist from Princeton University, and he studies galaxies. However, at the heart of every large galaxy, her work, is an object that we cannot even see. And her research is based upon those objects called black holes. So please welcome Dr. Jenny Greene, Princeton University.
All right, should be live. Good. Let me know if you have any trouble hearing me. Thank you all for coming tonight. It's a beautiful space, and it's a beautiful park, and it's a beautiful night. I was going to give you my normal talk about supermassive black holes in the centers of galaxies, and I will give you a little bit of that. But today is a special day because yesterday was the 25th anniversary of the launch of the Hubble Space Telescope. So let's see a show of hands. How many people have heard of the Hubble Space Telescope? Exactly. So this is a time of celebration for astronomers because Hubble is doing better now than it ever has over the course of my astronomical lifetime. It's incredibly healthy, it's incredibly productive, and it's 25 years old. And so the astronomers at the Space Telescope Science Institute in Baltimore have been preparing for more than a year for this event. And if you like what you see tonight, I encourage you to go to the 25th anniversary Hubble website, which has a whole bunch of educational materials and other things that you can enjoy at home. But for the first part of my talk, I just want to go through some slides that they actually prepared, and I've picked my favorite ones, just to really highlight some of the achievements of Hubble over the past 25 years. So most of this is not my work, but it's things that we can all enjoy together, lots and lots of eye candy, but feel free to interrupt me and stop me whenever I say something you don't understand. So just a tiny bit of history here about the time before Hubble was launched. It really started as a dream of this man here, Lyman Spitzer. He was a professor in Princeton, in fact, and he's known for many great astronomical discoveries and thinking. But one of the things he did in 1946, before the US really had a space program, was come up with this idea that if we put a telescope into space, of course, that mirror would be outside the atmosphere. And as you probably are aware, as light travels from distant stars, galaxies, all the way to the edge of the universe, before it can get to our telescopes on Earth, it has to travel through the atmosphere. And the atoms in the atmosphere are moving around, and that causes the light, instead of traveling in straight lines, to get deflected. And so instead of beautiful, crisp Hubble images, which I will show you, when we take pictures from the ground, they get smeared out by the atmosphere. And so the idea was, boy, just imagine the science we could do with a telescope in space. So in 1958, soon after the launch of Sputnik, I believe, the National Aeronautics Space Administration, NASA, was established. Then 1962, the National Academy of Sciences recommends a space telescope be a national priority for the US. The Europeans joined with us in 1976. And finally, in 77, Congress funds a large space telescope project. And that's when earnest. In fact, Hubble was completed in 1985. But because of the Challenger, it was not launched until 1990. So that's a picture of the launch. And here is the Hubble Space Telescope, April 25th, 1990, deployed into a low Earth orbit. Okay, so just some fun facts. It was in the Space Shuttle Discovery, weighs 24,500 pounds, maximum diameter 14 feet. It's a 2.5 meter telescope, though, 43 feet long. It's 339 miles above the Earth, and it goes around every 97 minutes. We can get data for about 50-something minutes. And so when astronomers sit down to think about projects that they want to do with the Hubble Space Telescope, we all talk about the unit of the orbit. While Hubble is going around and the sun is not in the way, that we can get data. So as you're probably aware, very soon after Hubble was launched, people realized that there was a problem. And there's a famous story from Princeton. So as I told you, Lyman Spitzer, who was a professor at Princeton, was really the person who dreamed up the idea of a Hubble Space Telescope. But there was another great astronomer at Princeton named John Bacall, who was very influential in getting Hubble to be built and launched. And so when the first images came, there was great excitement in Princeton because there was so much buy-in into this idea. In addition to John Bacall and Lyman Spitzer, there's also another famous astronomer named Jim Gunn, who was one of my personal collaborators and friends, who actually built one of the, or created one of the first instruments for the Hubble. And so all of these great men are together in a room, just incredibly excited over lunch about the first pictures coming down from Hubble. And they're all talking about how beautiful these pictures are, except for Jim, who apparently was sitting there with his head in his hands because he knew that something wasn't right, that the pictures were blurrier than they were supposed to be because the other guys, they were theorists. So in astronomy, we have this great divide between people who come up with the ideas and people who build the instruments and take the data. And Jim is an instrumentalist, and he knew that something was wrong. And what was wrong was the mirror was not exactly the right shape, okay? And it was something like, well, what's the number? 1/50th of the width of a piece of paper wrong. And yet that caused the original images to be blurry. Okay? And so astronauts went up into space and put something called COSTAR, which stands for Corrective Optics Space Telescope Axial Replacement, in to fix the vision of the Hubble. And they did so successfully. Okay? And so you get these absolutely beautiful, crisp images, of which we'll see many more in this talk. Subsequent instruments that went into the Hubble later had corrective optics put into place. So COSTAR ended up being unnecessary later in Hubble's life, but thankfully we were able to correct this small problem. I have one other anecdote, which is that you may or may not know that before we launched the Hubble, there were multiple other Hubble Space Telescope-like instruments in space looking down. So it was not new technology, but the US government was using very similar technology for perhaps less scientifically motivated purposes. And so I was sitting next to... Yeah. All we ever say in the astronomy community is looking down. And that's the euphemism. So I was on a plane and I was sitting next to someone from that community who was telling me basically that he knew the guy who had flipped a part in the polishing of the mirror. So some part got literally turned over, which caused the mirror to be the wrong shape. So it's really quite incredible that we've been able to service the Hubble Space Telescope, not just that one time, but actually 4 times. And this is a picture from the 4th servicing mission in May 2009. And I don't know, I have very clear memories of watching this all happen, and it was an incredibly ambitious servicing mission. They put in, the main goal, the planned goal was to put in a new instrument called the Wide Field Camera 3, which has been incredibly productive since it was put in 2009, and also a spectrograph called the Cosmic Origin Spectrograph, which looks at light all the way into the ultraviolet. And that's one of the things that Hubble can do uniquely. Because of the atmosphere, those UV photons don't go through the atmosphere. So if we want to understand this very high energy phenomenon from stars, from galaxies, we really need to take data from space. And so this was a new spectrograph as well. But in addition to those two things which were planned, also the Advanced Camera for Surveys, which was another workhorse of Hubble, had died unexpectedly. And so these astronauts also fixed the Advanced Camera for Surveys and another spectrograph, as well as installing 2 new instruments. And it was just amazing. So the Advanced Camera for Surveys died, I think the year before. I don't quite remember what year, but I do remember that, you know, the way it works is once a year, astronomers get a chance to put in proposals for science to be done with Hubble. So we all spend about a month leading up to that proposal deadline just frantically writing proposals. So the proposals are about 4 pages long, and we say, oh my God, we have this really big gap in our understanding, and the only way we can fill it is if we take lots of pictures with Hubble. You have to give me the time. So everybody writes their proposals, and this year 1,100 proposals were submitted about 3 weeks ago, I think. But so in 2008, we all submitted our proposals, and literally the next morning got the word that the Advanced Camera for Surveys was broken. So nearly half of the proposals at the time were for that instrument. And so we all had to go frantically work to rewrite our proposals to be done with the inferior instrument. It was a really sad day. So we were super excited when the astronauts succeeded in all of their endeavors. And as I told you, ever since then, Hubble's been just remarkably productive. And here's just a nice montage of science all the way from planets in our own solar system, which are just light minutes to light hours away, out to stars in our Milky Way galaxy. It takes the light from those objects years to thousands of years to reach us, nearby galaxies, and then all the way to the edge of the observable universe. And just absolutely stunning images. Now, one of the things that my husband Abe said he is often confused about when looking at these pictures is what do the colors mean? So, you know, we always show these absolutely vivid, beautiful colors, and you guys have a beautiful projector here. But you'll often hear people talk about false colors. So usually in these pictures, the colors are scientifically meaningful. So although what you're seeing is not what you would see with your eye, these pictures have been taken with multiple filters. Okay, so the light that you're seeing in the blue usually is light that's on the blue side of the spectrum of what we see with our eye. And the light that you see, the exact wavelengths of this light is not the same as the exact wavelength that was taken a picture of. There's information because the redder light is less energetic and the bluer light is hotter, is more energetic. So that's how we use these color coding to tell us physically what's going on. Now you heard about a hydrogen alpha filter that they have on the telescope here. Sometimes we look at pictures for very, very narrow wavelengths, and that's telling us, for example, where the gas is, how the gas is distributed. So sometimes the colors are telling us that kind of information as well. So the next thing that this this slideshow is going to do is step us out from, just highlight some of the exciting science Hubble has done from planets all the way out to the edge of the observable universe. So I really liked this picture. This is the Great Red Spot on Jupiter, which apparently has shrunk by a factor of 3 from the first picture in 1995 to 2014. So this is the greatest storm in the solar system, and I guess 3 Earths could have fit in it in 1995. But now we're down to around 1 Earth. Okay? So this is just amazing that over the course of our lifetimes we can watch these space weather changing. Also very exciting, as you know, is the question of where is water in other planets, so we can really try to understand where there's life outside of our own Earth. And so this is Europa, which is a moon of Jupiter, and what you're seeing here is an artist's rendition. What the Hubble actually did was take spectra, so spread the light out, and looking at lines of oxygen and hydrogen, figured out that there was, plumes of water coming off of Europa, probably being driven off by the magnetic field of Jupiter. So, next we're going to leave our own solar system and our own and to a nearby star. This is actually a pair of stars, Eta Carina, very well studied by astronomers because this is one of the most massive stars nearby, and it's in its death throes. So we think it's going to have a supernova any day now, like in the next million years. So maybe if we're lucky it'll be soon, but in astronomical time that's pretty soon. In any case, this just allows us to look at the anatomy of a dying star. And what you're seeing here schematically is again spectra. So this light was spread out by the Hubble Space Telescope, and you can see different elements: iron, nickel, argon, helium, and you can watch how these different elements are moving in these gigantic bubbles that this star is blowing in its death throes. So this is a just dramatic and beautiful picture. Has anyone seen this one before? This is one of the first pictures that captured the attention of the public from Hubble. These are the pillars of creation. So these are relatively nearby star-forming regions. And what's all this dark stuff? Is that because there are no stars? What are we seeing? Anybody know? Dust. Yeah, that's schmutz. Now, important is it's telling us that there's lots of gas and dust there. It's dense enough then that gas and dust is compressed and can form new stars. So these are buried sites of new star formation. And this iconic shape that many of you may remember from many Hubble pictures was taken with the Wide Field Planetary Camera 2, known as WIFPIC 2 by astronomers. But the public loved this picture so much that we looked at it again with the Wide Field Camera 3 in 2015. Isn't that spectacular? Okay, so that was the original. And these things are light years in length. Okay, and you can see sort of gas getting ablated from the edges of these star-forming regions. But it gets even better. So these are pictures taken with optical light that our eye can see. And the wavelength of the optical light is actually very similar to the size of the dust grains. So when the light encounters dust, it's scattered or absorbed. If you go to longer wavelengths, longer than our eyes can see, the next kinds of photons you find are near-infrared photons. And those are much less affected by dust. So why don't we take a look at the pillars of creation now, not just in the optical, but also in the infrared. Wow. Now you can see through a whole bunch of dust, and you can believe us when we say that those dark regions are because of dust, not an absence of stars. And these two views now, of course, allow us to learn a tremendous amount about how much stuff there is, where the stars are forming, the masses of the young stars, and so on. So that's one of my favorite pictures. It's another nebula, the Horsehead Nebula in Orion. And then let's just play the same game again. And there it is in the infrared, taken in 2013. Oh, apparently, is this actually a video? No. All right, zooming in now. This is again the Orion Nebula. And these little patches are tiny cocoons around forming stars. So this is the dust and gas that these stars keep around them as they're forming. And these dusty disks, we think, are the sites of new planets being formed. Which brings me to my next picture. This is a nearby star, and what you're seeing in this little tiny speck here is a planet. And it's taking 2,000 years to orbit Fomalhaut. And in fact, it's been seen by the Hubble Space Telescope multiple times in its orbit. And so you can imagine if we can start taking these direct pictures of planets around other stars, we can start to learn a lot about other solar systems. But we can do better than just take pictures. We can start to learn about the stuff that's in the atmospheres of these planets with the Hubble Space Telescope. And in fact, I believe the Hubble was one of the first instruments to even try this game. So star and planet, none of this is to scale, okay? Star is far, far brighter than the planet. It's incredibly difficult to learn very much about the planet. But a tiny little bit of light from the planet's atmosphere absorbs a tiny bit of light from the star. And you can actually detect that signature when you take a spectrum, when you spread that light out. And so you can start to learn about what kinds of stuff is in the atmosphere of the planet. Sodium, hydrogen, oxygen, carbon. And you can start to learn about conditions in that atmosphere. How hot it is, how dense it is, and methane as well. So this is a game that we're going to get increasingly good at playing with upcoming instruments, but already one of my colleagues, Adam Burrows, and some of his graduate students are making detailed models of where in the atmosphere these elements live, so we can start to learn about the conditions in planets around other stars. It's just kind of amazing. So I'm going to go from the birth of stars and young planets to the death throes of stars. So here's a planetary nebula, just absolutely beautiful. And this is probably started its life as a star not so different from our sun. And as it's finishing its life, it's ejecting material out back into the interstellar medium, the stuff between the stars, in these shells, which are just getting illuminated and form these absolutely beautiful nebulae. You go to more massive stars, they die in a more dramatic fashion. I'm sure you've all heard of supernovae, and this was one of the real laboratories for supernovae because it happened right in our own backyard. This is supernova 1987A, and it was discovered from one of my favorite observatories, the Carnegie observatories in Chile. And what you're seeing is a picture that the Hubble Space Telescope took, and you're seeing material that was ejected in this cosmic explosion when this massive star died. And in fact, the Hubble came back many, many times. This was taken in 1994. And it went back and watched as time went on, and you can see as this material surrounding the supernova got relit up as shocks were traveling out of the explosion. So we just learned a tremendous amount about how massive stars end their life, how stuff is ejected out of them as they die. You wait a little while longer after a supernova and you get a supernova remnant. So this is the Crab Nebula. We even observed the supernova associated with the Crab Nebula in 1054. Okay, so it was documented by the Japanese and the Chinese. And so now we see it as this beautiful nebula, and this is one of the examples where some of the colors are actually telling us about specific elements. And a good friend of mine, he studies where the silicon and iron and so on get distributed when the star explodes, and that allows him to trace back to the moment when the star exploded and try to figure out the actual mechanism that caused the explosion. So that's really fun. And there's a neutron star in the middle of the Crab Nebula that powers the whole thing. There's a supernova remnant in a different phase, not quite as spectacular. So in addition to studying individual stars in our own galaxy, Hubble allows us to study stars even in other galaxies. This is our near neighbor Andromeda. It's the other large galaxy in our local group of galaxies. And if you know where to look on a very dark night, you can see Andromeda with your naked eye. The largest contiguous image ever taken with Hubble. It's called PHAT, P-H-A-T. Okay, and beautiful posters. Here, this is probably for you to see, but if you can see this darker region, Hubble looked at that entire piece of Andromeda, and I believe in my notes it tells me this is 7,400 individual exposures taken with Hubble over 411 different positions. So that's incredible. The woman who led this program said that there was a big poster of Andromeda on a wall somewhere in her department, and she apparently spent hours standing in front of it trying to figure out where she was going to put Hubble for each exposure. And it's just been spectacularly successful. So you can learn about stars in all stages. Stars that are forming, stars that are old, stars that have lots of carbon in them, just all kinds of things. So that's a nearby galaxy where we can study individual stars. Let's go out just a little bit further now to the Whirlpool galaxy, M51. Now, let me ask you again, what are these dark streaks that we're seeing? Is that because there's no stars there? Nope, it's dust again. And so what is this dust and dark spots telling us? Those are all basically regions like the Horsehead Nebula, where the gas is more compressed and young stars are forming. And so these reddish regions are actually all knots of young, hot stars that are lighting up the gas around them. It's absolutely beautiful. Here's a galaxy that's a bit more mature. It's not making as many stars anymore. It's got this big round bulge, we call it, in the center. This is the Sombrero galaxy. Also very photogenic. Now, but life's not always. Sometimes two galaxies get real close together, and this is what we call a galaxy merger. And again, you can see all this dust and dark splotches, which are telling us that when two galaxies merge, the stars don't actually interact with each other because there's way too much space between them. It's like clouds of butterflies passing through each other. But the gas slams into itself between the two galaxies, and that causes the gas to compress, and again, causes regions of new star formation. So all here are regions like those pillars of creation where new stars are being formed as a result of this violent event in these antennae galaxies. This is what you would see if you zoom out, and this is what you can see with the Hubble zooming in on the central region of these two galaxies. Similar idea here, and this one's just pretty, right? So this one's you're supposed to see a rose. This is the flower, and this is the stem. And again, these galaxies probably have been dancing with each other and getting ready to merge for a while, and so you can see all this activity. The blue, again, are hot young stars that are forming as a result of the gas and dust being jostled in these galaxies as they pass close to each other. Now, I've been focusing on the bright parts of galaxies, the parts that are spectacular in a Hubble picture. But Hubble doesn't only take pictures. So this one's much, much harder to make into a pretty, front page of the New York Times kind of picture. But it's really, really cool. So here is the central bright part of the galaxy, like I've been showing. It turns out, and this is just crazy, but if you go out 5, 10 times beyond the size of the galaxy that you can see in stars, you find that there's all kinds of gas way out there that's moving. That's what's indicated by these arrows. And what we think happens is that when young stars are formed and die as supernovae, these explosions actually pump a bunch of energy into the surrounding gas and heat it up. And if you get a bunch of supernovae in the same place, they can be, all that heat can cause plumes of gas to actually expand all the way out of the galaxy, in this case in both directions, and cause these giant galaxy fountains. Okay? So you can study them is by taking pictures of them, and that's that red stuff. I don't know if you can see. Another way you can study that gas is by looking at a very distant object way, way behind this galaxy. And if you look at the light from that distant object, you will see that some of the light is missing where gas that's in the outer parts of this nearby galaxy is absorbing it away at very specific places corresponding to elements like iron and hydrogen. And that's what tells us that these galaxies are constantly ejecting gas, which then falls back down and forms new stars. And so there's this whole dynamic region way far from the galaxy that we can study thanks to the power of this UV spectrograph that was put in the fourth servicing mission. All right, so now let's get even further away. And this is the Hubble Ultra Deep Field that was released in 2014. And this is the obligatory picture of the full moon, just to give you a sense of how big on the sky this region is. So this is a tiny patch of sky, but you're seeing something like 10,000 galaxies. Almost every speck in this picture is a distant galaxy. Collections of maybe a billion stars, 100 billion stars. And taking pictures like this, staring at one piece of the sky for many, many, many orbits of Hubble allows us to see basically the first baby galaxies forming. The pieces of galaxies that eventually became galaxies like our own Milky Way. And we can study their shapes, we can study their colors, we can figure out how many stars they're making. We can ask, when did the first galaxies really form? And this is something that you could never do without the Hubble Space Telescope, because all these foreground galaxies would get in your way. Well, it's really powerful, and we can see back to almost when the universe started. So this is the last picture, and it's not showing up very well. But what you're seeing here is gravitational lensing. So remember that Einstein's theory of gravity tells us that matter actually bends space. And so light, as it's traveling through space, instead of going in a straight line like it likes to, can get bent by very massive things. So this is a galaxy cluster. And I don't know if you can see these very faint arcs here, but those are background galaxies. This. That's all the same background galaxy that's getting, its light is getting deflected and bent as it travels towards us. And so these frontier fields are one of the newest initiatives of Hubble, and what they're doing is they're letting us study in some exquisite detail these very, very young galaxies, because we can study them. Their light is getting magnified by this cluster. So here's just a quick summary of some of Hubble's discoveries. When we launched Hubble, here were some of the things we wanted to study. How far away galaxies are, the gas inside and outside galaxies, which I showed you we did very effectively. Understand how massive stars die in supernovae, understand the solar system, and understand supermassive black holes, which is what I'll tell you about in a little bit. But then it turned out that Hubble was so much more powerful and so much more flexible than we could ever imagine. And in particular, we didn't know this, but the expansion of the universe is accelerating, and there's this mysterious dark energy, which Hubble has allowed us to study, and really the whole field of studying planets outside our own solar system took off after Hubble was launched, and Hubble is just, more and more proposals every year are to study the properties of these extrasolar planets, and then just all these other things as well. So it's been enormously successful. And I'm going to stop there and transition to tell you about how Hubble really let us study supermassive black holes, but I'll pause here and see if there are any questions about Hubble.
When you speak of the dust, like the Eagle Nebula and whatnot, what actually is the dust? What element is it, or elements is it? Do we know?
Well, there's carbon. There are these things called polycyclic aromatic hydrocarbons.
Oh, those?
So actually, there's a man named Bruce Drain, who's a professor in my department, and he absolutely loves dust. For the rest of us, as you can imagine, it's a little bit of a pain. Because if we want to study something and there's dust between us and that, it makes it very hard, right? Because the light gets scattered by the dust, the color that we observe isn't quite right because of the dust, and so...
Do you make your best guess as to like the heat and the...
No, so our eye doesn't see in the near infrared. We're seeing in the optical. The colors that we use don't necessarily correspond exactly to the wavelengths that light was emitted at. We are using colors that allow us to bring out various, like I said, the way the data are taken, you take it through different filters. And so you're letting through, just a very restricted range of wavelengths for each picture. And then in software, we combine them all into one picture, which encapsulates a lot of information about where the light comes from in different regions of the galaxy, let's say. And if you only had near-infrared wavelengths, you might choose different colors to display that than if you had, UV, optical, and near-infrared. So the precise colors that you use in making the picture are not corresponding necessarily exactly to where the light came from, but the different colors that we use signal that light came from different physical processes, okay? And usually what happens is you have to read the figure caption to figure out exactly which color corresponds to what. Does that make a little bit more sense? Yes?
Do you know Hubble's battery was made of plutonium-238?
No,
Okay, because I know that was used a lot for a lot of spacecraft.
I don't know.
Because it's like, it has
What
like
was the
a...
question, please?
Whether Hubble has batteries made of plutonium.
Thank you.
I don't think so.
No, they don't.
Because a lot of spacecraft have it like that since, like, it's radioactive and, it lasts for like a long, long time, so.
There are solar panels, but I don't know
Okay.
what fraction of I don't know how Hubble is powered in.
It was the Cassini probe,
Oh, okay.
and they fought over that for years.
Okay. It's a great question, though.
Yeah.
1, 2.
Typically, once you get your downloaded data
Mhm.
from your time on the Hubble,
Right.
how many months or longer does it take for you to analyze that data and draw conclusions from it?
So I just got back comments on a draft that a postdoc I'm working on Hubble data that I got 2 years ago. That took a little longer than I was hoping. I've just gotten nearly all the data for the follow-on project for that one, so that counts as being behind in my mind. But one thing to know is that for regular programs, let's say you ask for 10 orbits, that's a typical size. Over the course of the next year, if you get approved, the data will be taken over that next year, and you will have a 1-year proprietary period, during which time only you have access to those data. After that, it goes to use them. Now, I just, as a signature of life. Is that what you mean?
As life as we know it here
Right.
anyway. How much has gone forward with that?
So, this is a very, very hard game, and people are playing variants of it. It's not my field either, so I'm hearing there's a hole at this point. But I think we're all hoping that next generation telescopes are going to be far more powerful, including the James Webb Space Telescope, which will be launched soon. To get more detailed information.
Are filters being added to that, say the Webb scope, to go above and beyond what we're already looking for?
Yeah, so, you know, I don't know which instruments are designed for this, but I do know that Adam Burrows, my colleague, has multiple students currently making models of atmospheres specifically for James Webb. And so they are not changing anything in the design of Webb anymore. They're just building it and getting it ready to launch. But the instrumentation suite will certainly allow us to do more of this kind of science.
Do you have any insider information on the illumination spots on the other small mini planet like Pluto that they've been looking at?
Series.
I
Yeah.
don't.
No. All right.
I'm sorry.
That's coming up.
Yes.
Stay tuned.
Yeah. I got a theory.
Yes.
Are there any whispers of another deep field study? To look at a spot in between
Another
the
deep
galaxies that are
field.
there for, say, 1,000 hours?
These frontier fields are kind of a different way of doing the same kind of science. And we're only about halfway through the frontier field. So that's really where Hubble is putting a lot of it. You know, the big programs. So I don't know what those will be, but they probably won't be quite as ambitious. So we're really trying to use this gravitational lensing as a trick to get even more information about those first galaxies. That's the trick we're trying at the moment.
You're looking at objects in space that a given object is at a given point in time based on calculation. It might have been from, you know, in the case of the early universe studies, from 13 billion years
Right,
ago.
so I should have said, of course, light travels at a finite speed. So whenever we look to distant objects in space, we're also looking back in time because it takes time for that light to get to us. And it could even be 10 billion years.
Yeah. This may not make sense because maybe nothing travels fast enough, but is there any, like, where you get an image of something and then that same something at a different point in its time, at a different point in space? Or does nothing ever...
Well,
In other
so
words, if
one
you
of
had
the
something that-
amazing things that came out of these frontier fields was that they actually caught a gravitationally lensed supernova. So there was a supernova in a background galaxy that was lensed by a foreground galaxy, so you saw multiple images of the supernova, and then it's going to show up. Again, this is all because the light's being bent by this cluster. It's going to show up in a different position later because the amount of light coming from the supernova is changing, and so exactly where it goes with time is going to... So there's a whole industry now for when we should look again for this supernova to show up again. So that's kind of like what you were just asking.
It is, yeah.
So we don't have a ton of time nearest and dearest to my heart, and that is the study of supermassive black holes. So let me see if I can get my other presentation to go now. We were very successful the first time. So, and of course, we've already talked a little bit about gravity, but you know, gravity is an attractive force between objects. It's the reason that we all stay on the Earth. It's the reason that planets all stay in orbit around the sun. And in Newton's picture of gravity, light has no mass, and so it doesn't know about gravity. But in Einstein's theory of general relativity, Einstein figured out that massive objects bend space. Light wants to travel in the shortest path, and so it can be deflected by massive objects. We've already seen an example of that with gravitational lensing. So you can imagine if you have an object that can bend light, then you could imagine putting so much stuff in such a small space, such high densities, that not even light could escape its gravitational pull. Okay? So if mass can bend light, then mass can trap light. And you can think about what we call the escape velocity, which is how fast does an object have to move to escape the surface of the sun? 620 kilometers a second. If it's not going that fast, it's going to fall back down. But if you imagine shrinking the sun, you're making the sun denser and denser, the velocity that you need to escape is going to go up. And if you make the sun 3 kilometers, so the size of Manhattan, then not even light, traveling at 300,000 kilometers per second, could escape. So a black hole is so dense, so much stuff in such a small space, that not even light can escape its gravitational pull. So that's what a black hole looks like. So the whole reason I went into astronomy to begin with was because even though we have these objects that light cannot escape, astronomers know that there are real astrophysical black holes out there. And that's because they're excellent detectives. Okay, so I just want to tell you briefly about some of the ways that we can figure out that there are real black holes out there in the universe. And the first way is that there are black holes that we call stellar mass black holes that are something like 10 suns. And these are the remnants of when very massive stars die. And every once in a while, okay, so as we know, when massive stars die, they have a supernova, and sometimes if there's enough mass, they leave behind a black hole, about 10 suns. And every once in a while, that black hole has a companion. It has a friend, a nearby star. And sometimes material from that star can fall from the star because of the gravity of the black hole onto the black hole. And when that happens, the stuff that is in the gravitational pull of the black hole, it can't fall right in because it has some energy. And so what nature does is it makes an accretion disk, and that accretion disk, the gas in the accretion disk kind of rubs up against itself and gets hot. And so the accretion disk emits light, and the stuff is able to accrete into the black hole. And so, at those moments where stuff is transferred from the star to the black hole, astronomers can find these black holes. They light up. There was no light there, and then all of a sudden they get bright. And so we say, oh, that looks like that's something pretty cool. And then you can go back and you can watch the star orbiting the black hole. And because this star is sitting near a black hole, it's not nice and spherical, but it actually gets spread out. It has this funny shape. And so if you look at the light from the star as a function of time, as you're looking at the side of it, you're going to see a lot of light. And as you're looking at the back of it, you're going to see less light. And so you see the light from the star go up and down. And you can use how long it takes the star to go around the object, just like you can use planets in our own solar system to figure out the mass of the sun. And you realize there's so much mass in such a small space that it must be a black hole. And I like to show this example because this is the first scientific paper that I ever wrote as an undergraduate. And okay, so that's the idea of finding black holes, but I'm interested in studying these exotic things called supermassive black holes. So instead of 10 suns, a supermassive black hole is millions to billions of suns. Now, how do we know about those? So the best way that we know, and this is my favorite movie in all of astronomy, is that we can watch individual stars orbiting the black hole at the center of our own galaxy. So now we're looking towards the center of our galaxy. We see all these beautiful dust lanes. There's tons of schmutz, not just a little, but tons, between us and the center of the galaxy. So let's zoom in now, all the way to the center, and we're going to watch stars going thousands of kilometers per second around the black hole at the center of our galaxy. And these are data taken over more than 20 years, I guess. I'm going to show that again. So you're seeing individual stars as they go around this red cross, which nature conveniently put on the picture at the position of the supermassive black hole. Let's see if I can get that to play again. There we go. And so why do I love this movie? Well, because, and we have much more data now, obviously. First of all, because, as I told you, there's a lot of dust and gas between us and the center of our galaxy. And to take these data, astronomers had to work very hard. They had to take pictures in the near infrared, where, as I told you, the light travels more effectively through the dust. And our technology has always been behind in the near infrared. And also, they had to go to the telescope every year and they'd take a picture of the positions of all these stars. And then they'd come back a year later and they'd take another picture, and then they had to figure out which star was which, right? Nobody was drawing these circles for them. They had to do that themselves. And because of how fast these stars are moving, they're able to figure out that there's a black hole there that is 4 million suns. So that is the best mass for a supermassive black hole that we know, and it's sitting right there in the center of our own galaxy. Now, it turns out that our entire galaxy, the black hole is only a fraction of a percent of the mass in our whole galaxy. So for us out here, 2/3 of the way from the center, we don't know anything about this black hole. Its gravity doesn't matter to us. The motion of the sun has absolutely nothing to do with this black hole. But for stars that are sitting very nearby, obviously, it matters quite a lot. And so then the question becomes, okay, well, we have a black hole at the center of our galaxy. How many galaxies have black holes at their centers? And so we can imagine using this very similar technique, that is, looking right at the center of the galaxy and asking how fast the stars are moving, to look for black holes not only in the center of our own galaxy, but in the centers of other galaxies as well. The problem is, other galaxies are much, much further away. And so you have to imagine looking at these same stars way, way further away. And so we can't actually look at individual star motions anymore. But we can look at the average motions of stars on very, very small scales. Now, what's the problem that astronomers have at looking at the motions of stars on really small scales? We talked about it right at the beginning, the atmosphere. And so this was a perfect application for Hubble. Hubble lets us zoom in to the very, very centers of other galaxies and ask whether the stars are moving so fast that there must be a supermassive black hole at their center. So now I'm going to show you another movie, now zooming into the center of a galaxy that also lives in our own local group. And you're going to see on the two sides how fast the stars would move with and without a black hole. Okay, so we're zooming in. This is M32. Sits on the edge of Andromeda. There are the stars. So you see how fast they move here with the black hole and how slowly they move there. Let's watch that again. So let's zoom in. Here are the stars very, very close to the center of M32. Really fast with, slower without. And that's the signal that the Hubble Space Telescope has been able to detect for something like 50 galaxies now. Well, okay, so there's Hubble again. Sometimes there's not enough signal from stars, So we can play the same game with gas, and the idea is the same. You're just asking how fast is the gas moving, here moving away from us, and here moving towards us. This is again data taken with the Hubble Space Telescope. And so the first thing that Hubble taught us is that the Milky Way is not special. Actually, all massive galaxies, everyone that we've looked at so far, contains a supermassive black hole in its center. So this is a common thing that galaxies do. And the other thing that we learned is that the mass of the black hole is remarkably tightly correlated with properties of the galaxy it lives in. So if you tell me the mass of the big galaxy, so something like, then I can tell you the black hole mass to a factor of 2 to 3. In astronomy, we don't know anything to a factor of 2 to 3. So this is really amazing. So I just wanted to, I'm going to skip through a few slides because here's just a picture as of a few years ago of all the galaxies that we've looked at for black holes versus their black hole mass. And so I just want to end with a little story for how we might get this relationship between black holes and galaxies, and it comes back to some of those beautiful merging galaxies that we saw earlier today. And so the idea is this. Anytime you have these two galaxies coming together with lots of gas, as you saw, the gas slams together and compresses, makes new stars, but it also funnels gas into the middle of the galaxy, feeds the black hole. So the black hole gets fed lots of gas and grows. So you're making stars and you're growing your black hole. And as the black hole grows, then the material in that accretion disk that's falling in is actually emitting more and more light. And that, an energy back into the galaxy, which is heating the gas, and eventually the black hole gets so powerful that it's able to drive another one of those giant winds I was telling you about, driving all the gas out of the galaxy. So all of a sudden, you've got a big black hole, you've got no more gas, you can't make new stars, you can't feed the black hole anymore, and you end up with what we call an elliptical galaxy, where there's no gas and dust, all old stars. And you can imagine if you repeat this cycle that you could get the black hole to just grow until it was just big enough that it could sweep all the gas out of the galaxy. And so our picture is that the black hole's growth actually is tuned to how much gas there is. And so it just grows until it's powerful enough to sweep that gas away. And that's what allows the black hole to talk to the galaxy, and so that they can grow in lockstep. And so we can just watch a picture of that happening. This is now a simulated pair of galaxies done by a graduate student at Princeton. And I'll show you that again. You're seeing the gas that's feeding the black hole, and all this red stuff is gas that's been heated by the black holes and is being driven out in a giant wind. Let's watch that one more time. Yeah, no, this may not be what you would hear if you were at the
Wind, I hear it.
And so at the end of the day, you've got almost no gas left and just an elliptical. So that's the story that I wanted to tell you about Hubble and black holes. And just to end, I want to show you one more movie. I know it's getting close to bedtime for some of you, including myself. So, as part of this 25th anniversary for Hubble, the Europeans launched a competition called Ode to Hubble. And they asked for movies celebrating the Hubble Space Telescope. You should go Google Ode to Hubble and you can watch some of the really awesome movies, including the winner. But this is not the winner. This is just the one that Abe and I like the best. And it will stick in your head.
Hit the expand.
Oh, yes, thank you. Uh-oh. Hubble, I love you. So as you know, the cameras are actually inside the telescope. The Hubble Deep Field. Servicing missions.
Causing it is fun.
Nebulae, Sombrero. Taking a selfie. Edwin Hubble himself. A rose.
Great tribute.
Thank you very much, and I hope you enjoy the rest of your weekend.
Any questions for Dr. Greene before you leave? Don't get up. Don't do it. Please.
Now for an
Except for
advertisement.
commercial.
Now time for a commercial break.
Just a few
Yes.
questions, and afterwards, get a little bit short. Take a couple more.
Perfect.
Like how many of the supermassive?
That's a good question. There could be, I don't know, maybe of astronomers at some point worry about supermassive black holes. It's an important part of galaxy evolution.
So, are you planning on taking any research from when they activate the Large Hadron Collider? Because they're trying to manufacture a black hole.
Yeah, that's really, really far from the kind of thing I worry about. I like to say that Newton does just fine for all the research that I do, because the stars are close to the black hole, but not that close.
True.
But yeah. Yep.
What inspired you to follow this career path?
That's a good question. So both my parents are biologists, and I went to the lab with my mom a lot as a little kid, and then I was a rebellious high school student, and I decided the one thing I wasn't going to do was science. I was going to major in anything but science. I got to college, and I did this whole Western canon class, and about in March, we were still trying to figure out whether or not we exist. And I thought, this is not for me. And I had taken an astronomy class in high school and loved it. And so I went to the astronomy department. I took one class. They said, look, we have more data than we know what to do with. We'll send you all over the world. And they did. They sent me to Chile for the summer, and that's what happened. Yeah.
How is the Hubble telescope maneuvered into position?
It was launched, and then a rocket. And then gravity took over. So it is orbiting the Earth.
So you have to wait, like for instance, if you want to see a certain planet, you have to wait for it to be in the right position or...
Oh, no. It's pointed at things. And then the first thing that happens before you start taking data is that it acquires what are known as guide stars. And so those are bright sources that it basically tries to keep in exactly the same position so that you have very fine controls over exactly what you're pointing at. Otherwise, the images would not look so pretty. Yeah?
Ma'am, you saw that like there are 4 million suns. So is this the final count or it has been calculated so far? The 4 million suns.
Oh, no, sorry. I meant per galaxy.
So per
So like our galaxy is something like 100 billion stars. And our numbers for exactly how many stars are in a galaxy are not very good. For one thing, as you probably know, it's pretty hard to figure out the exact distance to other galaxies, so that is an uncertainty. But then, you know, we see the light from the most luminous stars, and a lot of the mass is coming from stars that we can't directly see. So we have to make lots of educated guesses to figure out how many total stars there are in a galaxy. And then as you saw the gas and the dust get